Hi, class. So today we're going to talk about the chemistry of ground level pollution, or what I call more often air quality. So, in the United States and in developed nations, factories and industry used to be the largest source of air pollutants to the local airshed. But now, in places like Los Angeles, we think it's cars, and some new research by NOAA would have us think that personal care products. So if you smell someone in class right now, and you can smell their perfume or their Axe body spray, compounds like that. So in the biogeochemical cycling of the Earth system, the atmosphere is the oxidizing medium. And remember that when an oxidation reaction happens, it doesn't mean that oxygen has added. It means that the oxidation state of an element has gone up. And one thing I want to show you, this is personally satisfying, is this is from the Google News Lab. That was the source. It was published in Nature. And it was the top science terms that were searched for in Google. And in 2018, Air Quality Index was on there. And that's what we're going to talk about today. So we spent some time in class already talking about the ozone formation and the cycling in the stratosphere. We talked a lot about polar stratospheric clouds and chlorofluorocarbons, but in the troposphere, the formation pathways and the cycling is very, very different. So big picture, we have volatile organic compounds, which typically have short enough lifetimes that they're not making it from the northern hemisphere, for example, to the South Pole, like CFCs can, because their lifetime is so much shorter. So the predominant source in the atmosphere of organic compounds are plants and trees in the biosphere. So if you've ever smelled a Christmas tree or clean with pine sol, you've smelled these compounds. Sources of NOx include combustion from cars. So I thought that I knew what traffic was before I moved to the Los Angeles area, but now I really viscerally understand it. And when you have NOx emissions from combustion, it's usually pretty independent of the fuel source, and it's more a function of your burner efficiency. So when the Los Angeles DMV tells you you have to get your car inspected and you fail inspection, it's one of the things that they're trying to do is make sure that your air pollution and the amount of poison that you're putting in the air is below some threshold value. The other thing that surprised me is I moved to California from New Jersey, and these offshore rigs that you can see from the beach in California really, really surprised me. So, at the surface, usually at the surface, we have emissions of volatile organic compounds and NOx. And in the presence of sunlight, it kicks off these chain reactions that go on to form ozone and also other compounds. And here I'm showing nitric acid, which could go on to contribute to particulate matter. So ozone is a regional problem. It's not a local problem. When air pollution problems started happening, the journal that got a lot of the atmospheric chemistry literature published was the Journal of the Air Pollution Control Association or something like that. But now that journal went on and it changed its name, and I think it's the one that became Atmospheric Chemistry. And it marks this really important shift in the paradigms surrounding emissions of air pollutants and what goes on, what their fate and transport is. And so something that I always grew up knowing, even when I was an itty bitty atmospheric chemistry graduate student, but that the generation of scientists ahead of me was something that they had to tackle and come to an understanding, was that air pollution is not just a local problem. We all live downwind. And so when CARB, the California Air Resources Board, first started, when EPA first started, there was this traditional command and control approach to air pollution. The Code of Federal Regulations promulgates standards that define what it means to comply with the Clean Air Act, and they would say, you know, if you have this kind of stack, if this is your burn rate, if this is whatever, you can emit so much pollution. Now we would call those performance standards, but if you read old literature, you will see command and control. But now there's typically an airshed management approach where states who are impacting each other get together and they decide what the air quality targets they want to meet are, and then they take this more holistic approach. So in combustion of fossil fuels, there's generation of thermal NOx, and thermal NOx stands for NO plus NO2. As temperature goes up, NO goes up. So for this equation, NO2 plus O2 in equilibrium with 2NO, the equilibrium constant is low. And so NO does not easily revert back because the activation energy for the reverse reaction is very, very high. The yellow-brown color over Los Angeles and other smoggy cities is due to NO2, which absorbs in the visible spectrum at around 400 nanometers. And so absorption here removes purple, but it allows yellow to transmit. And we're going to talk about primary and secondary pollutants. Primary pollutants are air pollutants that are emitted to the atmosphere in the form that they're going to be in the atmosphere. But secondary pollutants are not emitted directly. So ozone is typically not emitted directly, rather it forms from precursors. So for example, NOx and VOCs go on to make ozone, and ozone is a secondary pollutant. Most particle mass in the atmosphere is also a secondary pollutant. And the reason why it's important to define that is if the Environmental Protection Agency or EPA wants to promulgate standards, they need to know, is the pollutant primary or is it secondary? So for example, in the case of particles, if that particle mass was primary, then EPA would make factories or whomever it was that was polluting put on particle control standards. But if the particle matter in the atmosphere was actually secondary, then EPA would promulgate certain sectors to have gas controls, to control those gases that go on to form particles. And so we talk a lot about primary and secondary pollutants, and it really comes from this need for regulatory agencies to define how they're going to attain the air quality that they want to see for people. Okay, so this slide, in case you're interested, it's a healthy reminder of Le Chatelier's principle, and it will show you the equilibrium of NO and NO2 and when you can see the brown color and when you can't. So in Southern California, after it rains and when it's really cold, you can see the mountains so clearly, and it's because the particles are washed out by the rain, and it's because it's cold, and if you watch this video, you'll understand. So what I'm showing here is an ECMA diagram. So the x-axis is the log of the VOC concentration, and then the y-axis is log of NOx concentration. And one thing that I want you to notice is that the units for the VOC concentration are ppbc. So what that means is parts per billion of carbon. So for example, if I had 1 part per billion of methane, methane has 1 carbon, so the concentration in ppbc would still be 1. If I had a concentration of 1 ppb of benzene, the ppbc concentration would actually be 6 because benzene has 6. In this plot, each of these black lines represents an ozone isopleth. It's very similar to a topography map if you are familiar with hiking. And so each black line represents a concentration of ozone that's constant over that black line. And what was really interesting is when EPA started trying to regulate ozone across the United States, strategies that worked in cities like Los Angeles were not working in some cities like Birmingham or Atlanta. And the reason why was that in some regions, the amount of ozone production was limited by the availability of hydrocarbons, or VOCs. And in other areas, the amount of ozone produced was controlled by NOx concentrations. So you could see that if you're in this area here, and say you have ozone of 120, you could reduce the VOC concentration by orders and orders of magnitude, but it would do absolutely nothing to your ozone. And so if you're in a city that would be somewhere around here, you want to control your NOx emissions. And in contrast, there are some cities where you could have a very high ozone, maybe here it's 80, and you could reduce the NOx concentration as much as you want, but ozone production here would be VOC limited and it wouldn't help you very much to attain your ozone. And that was very transformative when the atmospheric chemistry community finally got to realize what was going on and understand it. So a rule of thumb that we had, some of my colleagues and I at EPA, was ozone makes you sick, particles kill you. So an ozone molecule is an ozone molecule is an ozone molecule. But particles are physically diverse and they're chemically diverse. They have different sizes. Some are inhalable, some are respirable. And common constituents that we see across the United States is ammonium sulfate, which is a salt, ammonium nitrate, which is a salt, a variety of organic compounds, elemental carbons, and crustal species or dust. So there's different standards for fine particle matter. This is PM2.5. These are particles that are respirable. They make it into the deepest part of your lungs. On the top, I'm showing the standard of the World Health Organization, and they have an annual standard and a 24-hour standard. So the standards are 10 micrograms per cubic meter and 25 micrograms per cubic meter. So the annual mean can't be over 10, and the 24-hour average cannot be over 25. The U.S. Environmental Protection Agency also has an annual mean and a 24-hour standard, and the EPA standards are actually a little bit higher. So I want to ask you, who do you trust? And maybe think about why the World Health Organization and EPA might have different